Welcome to The Explainer. The internet. It's just there, right? We use it every single day. But have you ever really stopped to think about how it was all built? Well, today we're going to do just that. We're going to step into the shoes of the engineers who created it all. We'll look at the specific problems they were trying to solve, the tools they had on hand, and the absolutely brilliant solutions they came up with to connect our world.
So here's the game plan. We're going to journey through 5 key eras, and each one starts with a major real-world challenge that forced engineers to think in completely new ways, starting with the very first spark of electrical communication.
All right, let's rewind way back. We're in the 1830s, and there's a really basic problem holding everyone back. Information could only move as fast as a person on a horse. For a world that's starting to industrialize, that was just way too slow.
I mean, think about it. The world was speeding up, but communication was totally stuck in the past. It was vulnerable to bad weather, to bandits, to just plain human error. We needed something faster, something way more reliable.
Okay, now this is the fun part. Put yourself in the shoes of an inventor back then. This is your toolkit. You've got brand new batteries for a source of electricity. You know that running that electricity through a wire creates a magnet, and you've got lots of copper wire. That's it. So how would you use these pieces to send a message from one city to another instantly?
The solution they came up with was absolutely brilliant in its simplicity. Convert letters and numbers into a pattern of on-off electrical pulses, dots and dashes. Just like that, the telegraph was born, and it totally changed the world. But you know how innovation goes. As soon as you solve one problem, you're already dreaming of the next one. Sending text was great, but what if we could send our actual voices across that same wire?
Okay, let's jump forward about a century, into the 1950s and 60s. The world is a very different and honestly a much scarier place. We now have these amazing room-sized computers, but they're like these isolated islands of information. They can't talk to each other. And then the Cold War introduces this terrifying new threat that makes connecting those islands a matter of life and death.
Think about how an old-school phone call worked. It created a single, dedicated connection, a continuous circuit between you and the person you were calling. But here's the fatal flaw. If any single point on that long line gets destroyed, say by a bomb, the entire connection is dead. Poof, gone. For military command and control, that was a catastrophic weakness. We needed something that couldn't be killed so easily.
So the engineers had this totally radical idea. What if, instead of one fragile connection, we chopped our message into hundreds of tiny pieces, put each one in a digital envelope with an address, and just toss them all into the network to find their own way? That's the difference you see here. Circuit switching is one road. If there's a roadblock, you're stuck. Packet switching is a web of thousands of roads. If one is blocked, the packets just find another way. The messiness is the whole point.
And this quote from one of the key engineers, Paul Baran, just nails the philosophy. Don't build a perfect network. Build a network that expects to be broken and can heal itself on the fly.
And this became the beating heart of ARPANET, the grandparent of our modern internet. It's a simple 3-step dance. Chop the data up, route each piece on its own, reassemble it at the other end. And get this, the very first message they ever tried to send was the word login. But the whole system crashed after just 2 letters, LO. Now you might think that's a failure, but no way. It was a huge success because it proved the concept actually worked.
So by the 1970s, ARPANET was a hit. But it was like building an amazing highway system in just one country. Meanwhile, other countries, or in this case, other labs, were building their own totally different kinds of networks, some using radio, some using satellites, and none of the roads connected.
It was a digital Tower of Babel. Each network had its own rules, its own language for sending packets. You couldn't just link them together. It would be pure chaos. They needed a universal translator.
And that's exactly what Vint Cerf and Bob Kahn created with TCP/IP. It's the universal handshake that lets any network talk to any other network. You can think of it like the post office. The IP part, Internet Protocol, is just the address on the envelope. It gets the packet to the right computer. The TCP part, Transmission Control Protocol, is like certified mail. It numbers all the envelopes, checks to make sure they all arrived, and if any are missing, it asks for them to be sent again. It's the system that makes the internet reliable. And that's the thing. They built this incredible system to connect a few dozen research computers. As Vint Cerf himself said, nobody, not even them, had any idea what was about to happen. On January 1st, 1983, they flipped the switch.
making TCP/IP the standard, and the modern internet was truly born. So the internet works. It connects computers. Awesome. But there's a big problem. It was built by engineers for engineers. If you wanted to connect to another computer, you had to know its numerical address, something like 192.0.2.1. Yeah, that was never going to work for regular people.
So the first solution was something called the Domain Name System, or DNS. You can literally just think of it as the internet's phone book. It does one simple but crucial job. It translates a name that we humans can remember, like example.com, into the long string of numbers that computers actually use.
But an address book wasn't enough. The real game changer was making all the information on these computers easy to share and link together. And that's where Tim Berners-Lee comes in with the World Wide Web. Now, I gotta be super clear here. The web is not the same thing as the internet. The internet is the plumbing, the global network of wires and routers. The web is the stuff, the pages, the links, the pictures that flows through that plumbing. It's an application that runs on top of the internet. And with the web, the floodgates just blew wide open. The growth was explosive. We went from a few thousand computers online to millions and then billions. And suddenly, this led to a massive global problem that almost nobody saw coming. We were literally running out of internet.
See, the original address system, IPv4, had about 4.3 billion possible addresses. Now, back in the 80s, that sounded like an infinite number, right? More addresses than people on Earth. We thought we were set forever.
We were running out of room, so engineers came up with some clever workarounds. One is called NAT, and it lets your whole house, your laptop, your phone, your smart TV, all share one single public IP address. It's kind of like an entire apartment building sharing one single mailbox. It was a brilliant patch, but it was just buying us time. We needed a real, long-term solution. And that solution is IPv6. Now, just look at the difference here. We go from 4.3 billion addresses to 340 times undecillion. That is a number so big our brains can't even process it. It's a trillion, trillion, trillion. You could assign a unique IP address to every single atom on the surface of the Earth, and you wouldn't even make a dent. So yeah, I think we're good on addresses for a while.
So when you zoom out and look at the whole story, it really is like a relay race through time. Each generation of engineers gets the baton, they run their leg of the race, they solve a huge problem, and in doing so they hand a brand new problem off to the next runner.
So what's the secret sauce here? Why is the internet scaled in ways its creators never ever imagined? It all comes down to its core design. It wasn't built to be perfect, it was built to survive. It's decentralized, it's layered, it's open. It expects to fail, and it just routes around the damage. That's its genius.
This whole incredible story started with a couple of human needs: conquer distance and survive a disaster. We've done that. But today, the challenges are totally different. We're talking about privacy, misinformation, security. So the real question for us is, what problem do we need to solve now? What should we be building the internet to do for the next generation? Because that next chapter, well, that's being written by all of us right now.